Hello, everyone. Welcome to today's Ask the Experts presentation sponsored by Qualmark. I am Gail Eckert, Director of Marketing. I'll be your moderator for today. Qualmark hosts our free Ask the Experts webinars throughout the year featuring topics of interest for our accelerated stress test community. Today, Qualmark Senior Application Engineer, Neil Dortenbaugh, presents how HALT streamlines and improves accuracy of reliability prediction and testing. Meeting business needs while keeping pace with the speed at which today's technology changes amplifies the challenges in designing and developing new product. Meeting reliability requirements, enhanced lifecycle maintainability, and risk mitigation goals relies on a program designed to deliver accurate analysis and prediction. This presentation reviews how highly accelerated life testing can help you meet those challenges. Neil, would you like to get us underway?
Thank you very much, Gail. Yes, let's go ahead and get started. I think that the folks who are currently working in reliability engineering realize that we're facing increasing pressures, same pressures that are driving the rest of the industry. It's the faster, better, cheaper, impossible three that we're being continuously urged to meet. Things are getting to market faster, and they're more complex products than ever before that they're trying to get out. And often that means trying to compress test times, since those are happening near the end of the project development cycle. And they want to have improved accuracy. Everything is going faster than it has before, and the reliability of predictions become more important because money is becoming more important. Everybody's suffering with tighter budgets, and they want reduced test costs as well. And the last place you want to be is in a situation where you're barely getting accelerated live testing underway when marketing says we have to release or miss the marketing window. And more, these are the conflicts that are showing up in reliability engineering. And companies are getting much more sensitive about warranty costs. One of the ways to save money when there's a recession on and people are reluctant to spend money is to reduce warranty costs. This just gives you an idea of some of the warranty costs in millions of dollars that companies have been setting aside, and you see that there's a huge amount of money being spent on warranty costs. That comes right out of the bottom line. So anything that reliability can do to reduce warranty costs and more accurately predict warranty costs is of value to the customer. And if you're not doing it right, you may wind up heading out the door. So we want to be sure that we wind up more in situations like this, where we've got good MTBF data, we know what to expect from our product from a reliability standpoint before we hit market release. And ways that reliability engineering can make that happen is to make their failure mode effect analysis or the failure mode effect and criticality analysis more accurate so that liability risks are reduced. You get better ideas of what really might fail and what really is the result. And we've all been through FEMAs that are just agonizing, and sometimes you get surprised with failure modes afterwards. And to make those more accurate is a valuable thing to do. Another thing that reliability can strive to do is get faster results from their accelerated life testing and reliability growth testing. Those are time-consuming tasks. We all know that. And to be able to get good results from those more quickly would help meet those customer goals. And to get those outputs, the MTTF or MTBF information that comes out of the HALT and RGT, to have those be more accurate then saves money in warranty as well. So these are the primary things that reliability engineering can do in response to the pressures. The question is, how can we pull it off? And there are ways that HALT data can help in that process. If you've applied it properly, the failure data that you get from HALT can give you faster and more focused FMEA and FAMICA. You can also get ALT and RGT done more quickly and more focused on viable failure information, if you will, and as a result, get to those MTTF, MTBF predictions more quickly. Those things, with HALT feeding into those things, there's a great amount of value to be had from that HALT data. Now, I've found that as a general rule, when I say we're going to perform HALT or have you performed HALT, I find people define HALT in about 40 different ways. So let me step through how I have defined HALT and what I'm thinking about when I describe HALT. This is also outlined in detail in the Qualmark HALT guidelines document that is available on our website for download. So if you're developing your own in-house program for HALT, you want to have some guidelines to work with, those make a good starting point. But for those of you who are very familiar with HALT, hang in there with me, this won't take but just a minute. Here's the basic idea behind HALT. We're subjecting a product to increasing levels of stress. We will use thermal extremes, extreme thermal change rates, vibration, the 6 degree of freedom repetitive shock vibration, and then a combined environment where we're doing rapid thermal changes, dwelling at thermal extremes while we're stepping up vibration stresses. At each one of these levels, we will continue to increase the stress until we find, ideally, operational and destruct limits at each one of those stresses. A key part of HALT is that we are testing while under stress. You want to find operational limits, soft failures, the things that when you take the stress away, the failure mode goes away. And the effectiveness of that test is very important, and we'll get into that later and how it links in with the reliability testing we're used to doing. When you're in a HALT, you're finding failures, quickly eliminating them, working around them or ignoring them if you can, and continuing so that you get as much information as you can, stopping when we hit what we call the fundamental limit of the technology. And in HALT, that is the point where further improvement isn't practical or attainable without spending huge sums of money making fundamental changes in the product design. That's not what HALT's about. It's about eliminating the weak links before you get to that point. It's a repetitive process, HALT. You'll start with a stress, stepping up the stress to, and doing your full functional testing at every step, looking for failures. Once you actually find a failure, you'll do an analysis, see if you've got a soft failure or a hard failure, get some information back on it. If you're in the middle of a test in the lab, you're in a lab that that's not in-house, then you're more likely to do some kind of temporary improvement or somehow ignore that failure mode so that you can continue to increase the stress. And you keep stepping up, starting the process over from stress to stress until you hit a point, the fundamental technological limit. If the design engineer is there for the HALT and really understands HALT, then the fundamental technological limit will be the point where the engineer says, I can't do anything about this without making big, expensive changes. That's not what we're about. So we go until we find that fundamental limit, and we've cut out, basically cherry-picked out, all of the key failure modes in the product. here's another key. This is some of the fundamentals about understanding what HALT is. Number one is you don't pass or fail HALT. Technically, I don't think it's quite named right. The T is for test, and it's not really a test because you don't pass or fail. It's a process tool for design engineers to learn how their product fails. No pre-established limits. There's no point where you say, there, that's good enough, I can stop, I passed. The product tells you the limits. You keep going until you find that failure, and I'm going to say this 2 or 3 times, you have to be monitoring the product under stress. The functional test under stress is very important. Because we have a different purpose, not pass-fail, but pushing to failure, we use different stresses. We have the phrase stimulate, not simulate. That is, we're trying to stimulate failures, not simulate an end-use environment. So we will use temperatures beyond what the product is intended to be used in, what it's spec'd for, what the components are spec'd for. We're looking to find weakest links. Same thing with temperature change rates. We'll typically see 60 degrees C per minute change rates, far beyond anything it will see in the field, but it yields valuable failure information. And the same thing with the 6 degree of freedom repetitive shock vibration that we use. It delivers energy into the product in a way that it will likely never see in real life, but it's very effective for very quickly showing what's going to fail. Now, given that set of conditions, it's difficult to see how you can take what you get out of HALT and use it in a reliability engineering program where you're trying to get accurate MTTF data or MTBF data that relies on simulating end-use conditions. But there are good ways to take this information and help the basic reliability testing. The first point I want to talk about is change point analysis. For those of you that aren't familiar with the term, it's basically the idea, you rarely have a design that is completely new from the ground up. It is based on existing technologies, it's an improvement, it has added features, it has ROHS, it has some change that has been made. So change point analysis is the review of those changes. That will happen after you do the classic standards-based predictions. I know some companies have kind of given up on these where you feed in the bill of materials and use the Telcordia or whatever standards to give you an idea of the reliability of the system. It gives you a gross overview of the reliability and can show you what some of the critical subassemblies are. Unfortunately, it is necessarily limited in accuracy because you don't have any real data on the product itself yet, and the models have a real difficult time keeping pace with the density and complexity and speed of the devices that we're working with these days. Once you actually have parts in hand, then you can move away from the standards-based prediction and get into the more accurate ALT and RGT type of testing. But as I say, most new designs are really incremental improvements or expansions of those previous designs. So do a change point analysis. It's kind of like a very focused and limited FMEA. Let's look closely at what changed and see what risks are brought on by those changes. Change point analysis can quite possibly reveal some high-risk items. It can say, oh, wait a minute, we've made big changes in a piece of circuitry that's critical to the communications in this product. What are we going to do? At this point, it makes good sense to consider prototyping assemblies or even portions of a printed circuit assembly and doing HALT on that assembly. Talk to companies whose CAD software will allow them to produce a portion of a circuit board and will also produce the test point hookups and the signals that should be going in and out of those test points to allow a functional test on a small piece of a circuit card that is still in design. And they do HALT on those pieces to quickly see what's going on. You can focus on an area of concern in a subassembly HALT. If you have particularly a new vendor to look at, or you know that one whole circuit card has changed dramatically, get that one prototyped early and do a HALT on it quickly so that you can get real failure information on it. If you have historical data on the product before the change was made, especially historical HALT data, you can make comparisons to let you know at a gross level, have I introduced something that's going to be a big problem? Are there failure modes in this section of circuitry that I really need to worry about? This can facilitate the change point analysis process by giving you the confidence level to go ahead or giving you the red flag that says we need to look a little deeper here. And that can be good information to have before you get deeper into the reliability program. One of the key things that can happen as a change is a new vendor. If you get a new vendor in for a subassembly, often this is simply at the level of engineering change order. I've got a new vendor, but if I look carefully, do a change point analysis of what's going to happen, what might happen if I've changed this subassembly, it might give me cause for concern. A comparative HALT between two vendors is a real quick way to see if you are introducing a new risk. A typical HALT just takes a few days, 2 to 3 days for a HALT. And again, if you have that historical HALT data, it's very valuable here. You can say, gee, when I did HALT on my original product, my limits were such and so. None of it was due to this new display board that I have just purchased. So when I put the new vendor in, and it is indeed showing me new limits lower than what I had on my whole product before, I have reason to panic and start chasing things down and maybe reconsider this vendor. So as part of that change point analysis, if new vendors are an issue, a quick HALT can help you decide if that's going to be an issue. As you move on, get past change point analysis, and maybe you've done a few quick prototypes for that, now you start looking at the FEMA, FAMICA, and how my system might fail and what those effects might be. HALT is uses a similar concept in testing. The goal is to find out how your product fails. So there are common goals between HALT and FMEA and FAMICA, but they take different paths. Because they are similar, both failure-oriented, it is still a prediction. It's not predicting life, it's predicting failure mechanisms and giving you an understanding of failure mechanisms. So the results from each of these can facilitate the other. Of course, FMEA is started before you have cards in hand, but like the change point analysis, if these show you areas of concern, it can give you reason to get to prototype on those quickly. And FMEA and FAMICA typically straddle the line of theory and actually having first prototypes in hand. And there's information to be fed back from FMEA and FAMICA to make HALT more valuable as well. Now, as I said, FMEA will begin before hardware is available, and integration with the design team is very important at this point. The things are found, fed back for improvement or change before you have hardware in your hands. This same link with the design team is important with HALT results. So from that standpoint, the two tests are similar. You're finding things that might be issues and linking closely with the design team to see if there's something that can be done about it. The goal is to identify and eliminate high-risk failure modes before the design is finalized. Now, FMEA is often considered a test that is done, you check it off, and you're okay, and you forget it. Ideally, it can be a tool throughout the product life cycle, so that as you find failures, and whatever point you find failures, you can feed that information back, refine your FMEA, and have it be a tool for change analysis and other things, just like HALT can be. So the two serve similar purposes in your reliability program. One of the things that can come out of a FMEA, ideally will, is key areas of concern. So if I have a portion of circuitry or functionality that FMEA says this can be a big problem, I've looked at design changes and have said, I need some real data on this. This is another time when a prototype, it makes sense to build up a prototype, do a HALT on it, and see if it supports the logic to make a design change. And it can also, or your HALT should be specifically targeted to that area of concern. And here the functional tests become very important. Make sure that your functional testing will identify the effect that you're worried about. Often in HALT, people think about, I'm just going to run it until it quits, and failure means complete inability to function. Degradation analysis should be considered in here as well. And if the FMEA shows an area of concern in timing perhaps, watch what's happening in that area of concern during HALT, not only for an inability to function, but for degradation that you might not expect. That degradation has a distribution, and on the unit you happen to be testing, it will happen at a particular rate or at a particular point. Out of 1,000 units, 2 or 3 of them may fail out of the box. So degradation is a good thing to look at, and keep that functional test focused on what you're trying to find out, the particular part of the FMEA that you're trying to get more information on. Can let you know whether or not you're making a good decision. Now, we are using the polling feature in this meeting for the first time just to get some questions answered.
The poll question is, does your company typically compare test and field failure data to FMEA predictions?
Okay. The question is, do we go back and refine those FMEA predictions based on what I really see when I start doing HALT or when I get to field failures later? So that HALT data can give you a quick reality check. If your HALT is contradictive, it says the failure mode that your FMEA said was very likely to happen simply didn't show up, then let's take a closer look. Make sure HALT stresses are appropriate for the failure mode. See what's going on. If we get an entirely different failure mode, then we also have a reason to do further investigation. It's a way to get a quick check. Just in case you're curious, on the final results here, we have a majority of folks, slightly more, 44%, saying they don't feed that information back into their FEMA predictions, with 38% saying, yes, we do take the information that we get and feed that back to refine the predictions. So that's an interesting piece of information, I think. I've heard it said that it's a very good idea to take that information, feed it back, and keep the FMEA up to date and use it throughout the product life cycle. And that is what this slide is about. We want to keep the loop closed. An accurate FMEA is a valuable tool for the current design as well as future designs. When you start doing a change point analysis, having a good FMEA from a past design is good to have. Real failure information is the best stuff you can get your hands on. It sure beats theoretical failures. So put that back into the FMEA, it really increases the accuracy. HALT is often the very first real failure data that you have on a product. This is the first time you've had, your first chance you've had to see what's going to give out. So that data can get stuffed back into the FMEA quickly and quickly improve it. So to have that be better before you move on in the design cycle is a key value of HALT in the early reliability program. And a whole part of the failure recording and analysis process should be updating that FMEA with new failure data throughout the product life. At Qualmark, we emphasize the idea of having a fracas in place so that as you make design improvements, you're retaining that data for future designs, and you maybe do a subassembly halt. Any failure there, failure in accelerated life testing, reliability growth testing, a final halt, clear through to customer use, gets fed back in, understood, analyzed, acted on, and that information fed back into your FMEA. So now, for future designs, you have a good, solid database of what happens when your product fails and how it fails. Now, the results from FMEA can increase the effectiveness of HALT, and that comes from functional test. The whole ability of HALT to find failure modes is a function of, no pun intended, the functional test. If you can't find the failure, then you've wasted your time. FMEA can show you where things are most likely to fail, where tightest issues are, and where you can focus functional test software and where you might need to be putting in test points to catch signals and look at them and really increase the value of your HALT. Again, when you consider degradation analysis, if you are wanting to see, if you have the luxury of affording the oscilloscope that will give you a nice eye diagram of your critical timing parameters, then HALT, or the FMEA, will tell you where to look to watch for degradation that is the most critical. And if you're watching for that while you're doing your HALT and identifying what degrades, how fast it degrades, you can see if you have a need for improvement there. So the whole idea of finding failures and being failure-oriented in your focus in HALT as well as FMEA links those two together. The information you get from FMEA makes HALT more effective at finding failures. The information you get from HALT can make your FMEA more valuable earlier and give you better data for future designs. So that critical piece of reliability engineering work can be aided by selectively targeting HALT to the areas of concern. I've sort of used FMEA, FAMICA interchangeably. For these purposes, they are interchangeable. So now let's consider, as we move on through the tasks of reliability engineering, here are two of the key ones, the accelerated life testing and reliability growth testing. Of course, by now, you have product in hand. However, because of critical timelines getting tighter and tighter, people are pushing to start the accelerated life testing earlier so that we can have valid results before we release something that we're going to have huge warranty costs on. So there's a risk to getting HALT started early. And sometimes you're being pushed to use prototypes that may not be ideal for accelerated life testing. These early units might have design flaws in them that will slow down your accelerated life testing and corrupt the results of the accelerated life testing with failures that are going to be corrected before you ever get out the door, and so will not be a factor in true field life. The key is to use HALT first before you start accelerated life testing. As I said, HALT's a fast test. 3 to 5 days, you get handed a bunch of failure modes, and you can decide what to do about them. If you refine them and correct them in those few days, then they're not going to be showing up later in the early stages of your accelerated life testing. Unfortunately, the early stages of accelerated life testing can be the first couple of weeks, maybe 3 weeks, that you're popping up things that are meaningless in the end. And the data, if you can use it, is questionable. If you don't use it, you have fewer data points. So your life testing will happen more smoothly, and you'll be replacing fewer units during that test. One of the expenses associated with doing HALT is I have to use units to do HALT. That's very true. But that means that there's fewer units you're going to have to replace when you get into accelerated life testing. And that decreases the cost of accelerated life testing. And this point, the idea of actually being forced to restart accelerated life testing because you've had enough major changes in the design from what you learned in the early accelerated life testing that nothing's valid that you've done and you've got to start over. The chances of that happening has been reduced significantly by getting rid of failure modes before you get into your HALT. Accelerated life testing should be a demonstration of reliability and a source of valid life data. Your goal is to truly find out how long it's going to last, get some accurate numbers for MTTF and MTBF. It's too valuable of a tool to be used as a way to debug a marginal design. It's an expensive and time-consuming place to debug a marginal design. Debug the design in HALT. Take a few days to shake out the easy ones, and then get into that accelerated life testing. And as I talk about the idea of having to restart your accelerated life testing because of what you have found, I was curious to find out how many people have ever had to do that. If you get into an accelerated life test, you're a week, 2, 3 weeks down the road, and enough changes have been made that you have to throw away all that data and start over with the new product. And as those responses are coming in, I'm seeing about twice as many people saying, yes, I have had to restart, as opposed to, no, I've never had that happen. So that gives you an idea of the value that HALT can provide, because that's an expensive test to restart. And being able to get rid of those failures, get to the second rev of circuit cards without flying capacitors before you get into the accelerated life testing can be a very valuable thing to do. You can also accelerate your accelerated life testing based on HALT results. Now, when I talk about accelerated life testing at this point, I'm thinking primarily of thermal acceleration, where you're either doing testing at elevated temperature or doing temperature cycling. Before you've done HALT, you don't really know what your product's actual thermal limits are. And the interesting point is they're typically far outside of product spec and far outside of your component's stated operating ranges. This is data that you see presented here is from a study I did in 2008 of HALT tests that were done in the lab at Qualmark. It was over 47 tests. We found the lower operating limit thermally to average minus 48 C, and the destruct limit averaging minus 66 C. You certainly aren't designing, I bet maybe 1% of the folks that are logged in are thinking that their products are designed to run at these extreme temperatures, but we show that on the average they do. Many push the limits of the chamber cold. Hot, we typically see things running up to 90 C with destruct limits over 100 C. What your product can actually tolerate is much higher, can be much higher than what you have spec'd at, and consequently much higher than the limits you may have chosen for your accelerated life testing. You don't want to choose limits, thermal limits to accelerate testing that are going to induce failures you'll never see in the field or that are going to cause your product to malfunction right off the bat. So you may choose those conservatively to keep the test results valid. If you have HALT data, you can be somewhat more aggressive about picking your levels for accelerated life testing. The higher you can run it, the more aggressive you can be with those results, with those levels, then the more quickly you can get results from your accelerated life testing. It makes it all less expensive. Once you've understood those failures also at the operational limits, you will have failures that cause your operational limits to be where they are. You know what those failures are. If they actually show up in your accelerated life testing, you can say, this is an operational limit of my product. Maybe I do need to back off my stresses a little bit. I understand why this failure mode happened. A successful HALT also, once you get done, your limits are due to the technology. And those limits tend to have a pretty sharp, clear, low cutoff. So you don't have to worry about a wide distribution on that upper limit interfering with your accelerated life test results if you are going to higher levels. I assume you're seeing the slide here that is the full conclusions. We have 51% saying yes, we have had to restart HALT, and 32% saying no, we haven't. So that's a fair number of tests that could potentially, we can reduce that yes column significantly by doing a HALT before you get into your accelerated life testing. This gives you an idea. Many of you have seen before this diagram as we describe HALT, and we talk about here is a stress level, or we're applying some stress to your product across this axis. The green is the operational specs for your product. What this curve represents the operating limits for your product that we found in HALT. We found it at one point, or 3 or 4 points, depending on how many units you tested. We assume some sort of distribution around it. Normally, for accelerated life testing, you'll pick a level of stress, typically maybe somewhat outside of operational specs in order to get some good acceleration. But if you've got HALT in place, HALT results known that tell you I can come clear out here on the units I tested without hitting my operational limit, I can safely push out to some more aggressive HALT levels and get tests faster. Now, as I said, these discussions I've been thinking about thermal. The vibration stresses that are applied in HALT are dramatically different from those that are seen in real life, as I've described. It is difficult to correlate that to the accelerated life test that you may do from a vibration standpoint, where you're trying to basically take a PSD, increase those values, and get an accelerated vibration test results. You can make some generic conclusions based on how your product performed in vibration as far as operating and destruct limits are concerned versus what it saw in the last iteration the product and make comparative decisions that way. And if you comparatively find that you are much more rugged vibrationally than you were before, that tells you maybe I can accelerate my vibration life testing more by going to more aggressive levels. And now let's talk a bit about HALT as a component of reliability growth testing. This is really logically where it fits in most neatly to the standard reliability program. Many people, after I describe HALT and their hardcore reliability folks, say, oh, that's a test, analyze, and fix. I am finding failure modes and fixing them and continuing on. And that's exactly what's going on. And the trick is that it can give you that information more quickly and before you get into the formal reliability growth testing. I like this failure mode. You can see the cracks here on these leads, and these leads have actually pulled out. This was a RoHS issue, and as these loosened up and pulled out, the chip started to lean up, and these leads then started breaking off. So we had a good time with that one. If you get HALT done and eliminate those failure modes before you get into what I call the formal RGT, where you're tracking numbers to get MTBF data, the number of failures that you find in RGT will be reduced. That means it moves faster, and that means you're replacing fewer units. And the MTBF data that you're getting won't be distorted by those design-related infant mortality issues. Not really infant mortality in time, but infant mortality in design maturity. So you're getting rid of the failure modes from that are design-related and getting true life data out of your MTBF data. So it becomes more valid. The piece that you're being asked to provide is more accurate and gets done faster and cheaper. I've talked about the idea of doing HALT on subassemblies, HALT on full-up assemblies. This question is really for my information, and of course we'll share the results, but does your company typically, if you are doing HALT, do HALT just once on that final configuration product, or do you HALT subassemblies, or maybe, as I've described, portions of subassemblies in order to get more value out of the HALT earlier in the design cycle? So, in conclusion and in summary, HALT is a tool in a reliability engineer's toolbox. Just like if you've heard me talk about design verification testing, and I say HALT cannot replace design verification testing. HALT does not replace the reliability engineering tasks. It is a tool to make those tasks go faster, smoother, and be less expensive to do. When you do a change point analysis, when you are feeding data into FMEA, FAMICA, when you have to do your ALT, RGT, all of those can benefit from data that comes out of HALT.
Response. This is a perfect opportunity to remind you that Qualmark's website provides lots of useful information on HALT and HASS and how our technology can help you increase product reliability, accelerate time to market, and reduce warranty costs. You may find the white papers and previously recorded webinars in our library especially helpful. Again, thank you everyone and Neil for attending Qualmark's Ask the Experts presentation today.
Bye.